Welcome to the Magnetic Accelerator activity. So hopefully what you have in front of you is this activity called the Magnetic Accelerator, which is two front and back pages of questions that go along with the little experiment that's here. So the fact that you have this video means that you're not able to be in class today, but you can still view what this experiment looks like. So in following along with this, the introduction suggests that we should attach 3 balls to the right side of the magnet and then have 1 ball incoming from the left side. So we take one of the magnets here and then we can take 3 ball bearings. And what you'll see is when I roll this one in over here, it gets attracted by the magnet and pulled in. And that one also gets pulled in, and this one also gets pulled in. Although I would say that the attraction was the greatest for that first one to attach. Okay, so now what I'll do, so I'll take this ball and I'll give it a little push this way and we'll see what happens. Nothing, because I didn't push it hard enough. Let's try again. Okay, so you saw something pretty cool there, and you can probably just rewind the video and watch again, but I'll do it again. So we got 3 balls on this side. I'll come in with 1. And what you see is that this ball on the left gets pulled in by the magnet, and this ball fires off with a lot more speed than this original ball came in with. So this is what we're going to be investigating. So the first couple of questions, question 1, 2, and 3, get you thinking about this system and the energy that comes along with this, and thinking about things in terms of magnetic energy as well as kinetic energy. Question number 4 is going to ask you to try to draw a diagram of this. Now, we haven't really looked necessarily at these types of diagrams in class, and I'm not sure if you did these in Physics 1, but maybe an energy bar chart might be a good approach to this, where you can show bars, a bar chart, sort of like a histogram, where the histogram bar is higher when the energy is greater and lower when the energy is less. So that could be a good way to represent this energy. And then based on these pictures, we're going to then be able to make statements about strong bonding and weak bonding. So at this point, actually, I'll have you pause the video and you can look back again at that first case that we saw here to answer some of those questions. And then after you have completed number 5, you can come back and continue the video and we'll move on to the next part. So now we're looking at question number 6, and it says, we're going to try to explore what happens if we roll a glass marble slowly towards this initial setup. Now, interestingly, I was not able to actually find any marbles, glass marbles in the supply here. So I'm gonna have to try to cheat a little bit. And I have a wooden die, so obviously that's not a marble and it can't roll, but what I can do is I can push it into this setup. Okay, so no, as I push this in, nothing happens. The ball is not being attracted in. So this initial energy that I give it isn't enough. But if I push it a little bit harder, and I have to hold on to this so that the whole thing doesn't slide, but if I give this a good push, I gotta get it just right, apparently. Let's put another ball in here. Gotta get one that's not attached quite as strongly. There we go. So now I'm able to, with enough initial energy that I come in here with, even with something non-magnetized, what I can do is I can still knock this ball off. So this is gonna get us to now thinking about question number 6 and then question number 7 and how to respond best to that. All right, so at this point, I would suggest pausing here and you can consider those questions. Okay, now on the next page, we're going to be actually applying this to an important chemical reaction, ATP hydrolysis, and taking this idea of actually having, if I come to this, this is sort of our 3 phosphate groups, and that we have another ball come in, and that ends up being the breaking of ATP and removing one of those phosphate groups and having energy involved with that that group that's been released. Now, it's not quite as straightforward as this. This is just a model to help us consider what's going on, but we can learn a lot from thinking about the energy considerations of this model. So you can go ahead and try to answer some of these questions, 8, 9, 10, 11 through here, just based on applying the ideas we thought about in this model to now this chemical reaction. And you may have to relook up some ideas from chemistry class, possibly. So this could be a good time to pause the video and then consider those questions, and then come back when you're ready for question 12. All right, now looking at this, we have question 12. So ATP hydrolysis is an example of an exothermic or exergonic reaction. Now, can we find a way to demonstrate an endothermic reaction? So an endothermic reaction might be something that we would consider where you need a larger amount of energy in, and you actually end up getting a smaller amount of energy out. And actually have you pause here to consider what that might look like. So maybe pause and draw an example of what that could be, and then unpause when you have that. Taking a look at the situation. So what we have here is, in this case, and we can do it with just 2 here, and 1 comes in. So you have a case where if you've stacked more balls on the right side than on the left, that seems to produce more energy out. So what if we would do the opposite? What if we would have more balls on the left side and fewer on the right? So then we could come in with a ball on this side, and nothing happens this time. Take another one of these off. You try this. Nope, nothing happens. We can't get that ball off. But as you saw with the case where I slid in the so-called marble, the die here, if I slid it in hard enough, I could still get that ball off. So now we just need a way to be able to come in with more energy in order to remove that. So now in question number 13, in the previous text leading after that, we consider a phosphorylation reaction. We can take glucose and we have the metabolic breakdown of glucose. So now this is going to be a reaction that is an endothermic or endergonic reaction. And question number 13 has you thinking about this particular scenario. What happens if we set it up like this and we bring in a ball from the left? What's the final case going to look like? So I'll invite you to pause here and make a sketch of that. Okay, now that you've returned, we'll go on the number 14, and we're going to give this a try. So if you were here, you would build this, but I'm going to build this one, and I'll bring the ball in, and we'll see that it does not occur spontaneously. All right, so I need 1, 2, 3, 4, 5. I need 5 balls on the left side and 2 on the right. Oh, we're almost here. So bring in that one, bring in that one. Obviously, this is not going to work because otherwise you would have seen one of those work. So yes, indeed, nothing happens. That ball stays stuck on there. So what can we do? What can we do in order to get that reaction to occur? Well, what this suggests is that if we can couple it with that ATP hydrolysis, where we had, if we have a net negative change in energy, it's that net negative change, that's where it's saying that energy is being released. So if we can have a reaction that occurs, a coupled reaction, where first there is an exothermic reaction that provides energy to drive an endothermic reaction, that's going to be what we need. So that is our second reaction. So what we really need is to bring in a second magnet here. And we're going to set up the first case that we considered. So we'll put the 3 of these on, and then let's see if this works. I'll bring in a ball from the left here. And that was really fast. But what you saw was indeed this second ball came up. Oh, okay. Now they're jumping around. This is a lot of fun if you get to play in person. I'm sorry you were not able to play in person today. And what's the initial 1 and 3? I've already forgotten. Yeah, the initial was 1 and 3, or it could be 0 and 3. Let's see, is it enough if we do 1 and 3? So we come in. Nope, that wasn't enough. So if we want to make this, we need more energy to come out. So we need to take this ball off. And then when we come in, and just so you can see this ball flying off, and maybe you can slow it down. I'm sure YouTube has features you can slow the video down. Yep, indeed, this second ball had come off. So there we go. We have a coupled reaction that can drive an endothermic reaction to occur. Okay, that's it. So you can finish up this worksheet by answering these last two questions, 14 and 15, and that'll do it. Hopefully you've learned a little bit of interesting physics. This is kind of a fun energy consideration, a fun little activity to get us started with this semester. Obviously not quite related to all the other topics we'll go into, but I think it gives you the flavor of applying physics principles to biomedical applications.